Let's see, the next speaker is Krishna Balasubramanian.
Thanks. Thanks. So I'm Krishna, and I'll be talking about normal approximation for stochastic gradient descent. And the ingredient that I use is non-asymptotic rate for Martingale central limit theorem. And this is joint work with Andreas Anastasio from London School of Economics and Murat and Dogdu from Toronto. So the problem is as follows. We have a standard stochastic optimization problem where you're minimizing the expected value of some random function, which is denoted by big F, and y is your random vector and theta is your parameter. And the goal typically in SGD is to give a point estimator for theta star, but what we are considering here is not just give a point estimator, but give confidence sets for estimating theta star. And specifically, we want to use stochastic gradient descent to construct such confidence sets. And just to recall, the stochastic gradient descent is an iterative algorithm, which is given by this recursion here. And the G of theta t here is just a rough estimate of the gradient based on the point theta t minus 1. And usually it's based on one sample, and which is why it's typically an online optimization algorithm, right? And typically, Polyak and Ruppert in the 1990s also suggested to average the iterates, not just take the last iterates. So we denote by theta bar the average of all the iterates after t steps. And what is known about this algorithm, we know that if eta t, the step size is chosen appropriately, almost surely we have the theta bar converging to theta star. And most of the focus on the machine learning literature in the recent past has been on giving non-asymptotic rates just for the estimation error, like some norm of theta bar minus theta star, mostly in expectation and sometimes in high probability recently, right? What is known about inference, Polyak and Juritsky in 92 and Ruppert in 98 basically showed that if you scale the iterates, if you scale the average with a root t, it converges in distribution to a normal random variable with variance given by what is displayed here. And this variance is basically what is given by the Kramer-Rao lower bound. So stochastic gradient descent basically is an online algorithm which achieves the Kramer-Rao lower bound for parameter estimation, right? And the way this is proved is based on using a Martingale central limit theorem, which is asymptotic in nature. And related results have also been proved by the people that I mentioned here, and some recent works have extended it to like variants of stochastic gradient descent in Taulis and Iroldi 2017, and Ducci and Ruan extended it for like constrained optimization problems and things like that. So there's one issue though here to do practical inference. The asymptotic variance depends on the unknown parameter theta star. But recently, there have also been bootstrap style algorithms which are online in nature, which does not require the knowledge of theta star. So you can pretty much get an online confidence set. But the issue with all these approaches is that the validity of such constructed confidence sets are justifiable only asymptotically. So what if the dimension of the problem d and the number of iteration t is non-asymptotic, and if you want to jointly characterize the dependence on d and t together? So no such results exist to the best of my knowledge. And that's where our work comes in. We want to provide non-asymptotic framework for uncertainty quantification. So as I told, even for the asymptotic setting, the main ingredient for proving asymptotic normality was a Martingale central limit theorem result. So the first step that we have to do is develop a non-asymptotic version of multivariate Martingale central limit theorem. So just to give some definitions, we have x1 to xn be some multivariate d-dimensional Martingale random vectors. And sigma k, we denote the covariance condition on the previous filtration for the random vector xk. And by Sn, we denote the sum, and sigma and the variance of the sum. And we also have this partial covariances which show up when you're analyzing martingales. So one slight difference, if you're aware of the notations, is pk here we denote as a summation of the individual covariance from k to n. Right? So based on this definition, our first result is as follows. For a twice differentiable test function h, if you scale the sum appropriately by sigma n to the negative 1/2 and consider the expectation of that minus the expectation of the same test function applied to a standard normal random variable, z, the distance is bounded by the expression that is given here. So the constants here are also unimprovable. The rate here, the dependence on d in terms of square root of d is unimprovable based on our proof techniques, which is based on Stein's method. So just to give you a much handleable or a useful bound, if we assume that the sigma k's are positive semi-definite in this sense between alpha and beta, and if we make a third moment assumption which appears in this master bound here on the Martingale's xk, which we assume to be of the order of d to the 3/2, then the overall rate is controlled by d squared over root n. So this is what I meant by jointly characterizing the dependence on dimensionality and the random, number of samples n. Right. So as I told briefly, the proof technique is based on Stein's method, predominantly along with combining that method with Lindeberg's telescopic sum argument. And most of the assumptions that we made could be relaxed. For example, the sigma k need not be bounded away from 0. The bounded away from 0 could, the lambda min of sigma k need not be bounded away from 0. That could be relaxed. And we also crucially made an assumption that P1 has to be sigma n almost surely, which we were able to also relax that assumption. So applying these bound to basically get some bounds for SGD, we have the following results. Before we analyze the full version of stochastic gradient descent algorithm, consider just a simple linear system of equations. So you have a matrix, positive definite matrix A, and you want to find the solution to the system A theta is equal to B based on the stochastic iterative updates. Here yt is like a stochastic gradient descent, which is defined here. And the zeta t is a martingale that we assume zeta t to be a martingale. And theta bar, as usual, is the average of the iterates. In this case, if you assume that A inverse V, A inverse is between alpha and beta, positive semi-definite between alpha and beta, and your martingale's third moment is bounded by 3/2 based on the previous assumption, then we have the distance bounded by 3 terms. The first term comes from our previous martingale result, and the second and the third term basically comes from the stochastic gradient descent updates. So the dominating term is basically d squared over root t. That's what you want to concentrate on. And we also have in the paper a result for the stochastic gradient descent with strongly convex objective functions, and you could take a look at the paper for the result. Just to summarize, in this work we provide non-asymptotic rates to normality for stochastic gradient descent, and the main ingredient is developing a multivariate Martingale CLT. After our COLT submission, we were also able to extend the Martingale CLT result for not just twice differentiable test functions, but for Berriesian type of upper bounds. So we did that by constructing careful twice differentiable test functions that approximate the indicators of convex sets pretty well. And as usual, we saw that the rates are pretty bad in terms of dependence on dimensionality. So one practical case where this could be applied is when you only consider the infinity norm of the vector that you estimate. Like it's called as max statistics in the literature. So in that case, we are able to derive faster rates, which depend only logarithmically on d and not polynomially on t. And that concludes my talk. Thanks. So actually, Stein's method works only for differentiable functions or smooth test functions. So once we have that bound, we approximate indicators of convex sets with smooth functions that are carefully constructed. So that part is functional analysis, basically. Yeah. If you go to the Martingale CLT result, the root D here will be, even in the Berry-Hessian bound, it will be D to the 1/4. Here we have a D to the 1/2. So that's inherent, I believe, for martingales.